Okay. So first, an announcement that assignment 3 will be out today at 6 p.m. And as usual, it will be due a week from now at 10 p.m. Okay. And it'll cover lectures 9, 10, 11, 12. Okay. All right. And last class, we talked about an application of low rank approximation to matrix completion and how you can combine SVD with gradient descent and some other variants. And then we started discussing the new topic, which is privacy, right? And we first said, okay, privacy might seem easy. You can just do some anonymization, but that doesn't work. We saw various examples of that. And then we kind of made an attempt at least getting some kind of trade-off between accuracy and privacy for a simple enough setting, which was this randomized response. Right? So you're just trying to collect some survey data where each the database just contains things which are 0 or 1, and you want to release the mean. Okay. And what we're going to do today is start this study. One of the more well-defined models of privacy, which is differential privacy, and which is perhaps the most promising approach to privacy that we currently have, and discuss some algorithms that are used there. Okay. And as I said, the things that we're going to discuss are going to be more stringent on privacy, meaning they offer pretty strong guarantees, but as a result, you might lose something in data set sizes and accuracy and so on. And we'll study those trade-offs. Okay. All right. So what is differential privacy? And the first thing about differential privacy is, what I'm calling differential privacy is actually not just differential privacy, it's the central differential privacy model. Okay. I mean, I'm going to omit the term central. You can imagine there's like local differential privacy, there's hybrid differential privacy, and many, many other forms. And it's also sometimes called the trusted curator model. And maybe this is too strong an assumption in some cases, but to get us started to define things, I think it's a good model. Okay. And it's reasonably applicable in many settings. So what's the trusted curator model, right? So imagine the following setup. You have n users, user 1, user 2, all the way up to user n. And each person has some data that they have available. Maybe their search history, their demographic history, their medical history, something like that, right? Each person has some data that they have available, and think of, for privacy, the way we're going to study things, don't think of these as vectors for the time being, just think of them as coming from some set or domain X, okay? And in the trusted curated model, you're assuming that, all of these people share their data with a trusted person, like completely. Okay, so this is the trusted curator model, meaning I'm sharing all of my data with this person, right? You can easily imagine user 1 is my ratings of the movies, and I am obviously sharing this data with Netflix, right? I'm releasing it to Netflix in that sense. I'm trusting Netflix to do something, not do something untoward with that data. Okay? But then where does the privacy come in? Now, imagine the trusted curator will build a wall or some interaction service or some API to the database, right? This is the database. Okay. And then you have your, ML, algorithms, maybe various data scientists and so on. Okay, they're sitting on this side of the wall and they can interact with the database by asking questions and getting answers. So they don't get to see all of these things, but they have to submit a question and then they get an answer. Okay. So that's the trusted curator model, meaning there is a trusted person who holds all of the data records, but then the interaction with the ML algorithm or your model or your as a data scientist, whatever API you have, will happen through this curator. You ask that person a question, that person decides to answer it some way or the other. So you can imagine I send a question, and that's where the curator's task comes in. What answer should that person give? Right? So you can think of what is the curator doing. Curator needs to have a function or a mechanism M which takes the database as input. It could depend on all of these things. Maybe the data scientist wants to know, okay, what's the average of the first coordinate across all of the users? Maybe the first coordinate is a salary, right? I ask, okay, can you tell me what is the average salary among all the people in the United States? Okay. And the curator then needs to submit an answer. Right, so this is the database. And this is the answers for the query. You typically think of a database as a vector collection of vectors. Okay. And answers is, maybe binary, maybe they're real numbers or something like that. Right. So you can imagine maybe the curator is the US Census Bureau. It collected a bunch of statistics. It has a lot of information, age, salary, education, political leanings, voting record, or voter registration information and everything. And then the way you can interact with the Census Bureau is they have an API where you can say, tell me the average salary within San Francisco, within this zip code. I mean, you can actually find this information. There's Department of Labor, which releases all of this information. Okay. But you want this to be done in some private way. All right. So we are the curators. We are taking the role of the curators and have to decide how to answer the queries. Of course, the straightforward thing is to give the exact answer that you want. Meaning, if you ask me the average, I tell you the average exactly. But then it might leak information. Right? That's what we are worried about. Okay. All right. So how do you define privacy, or what kind of algorithms could the curator use which would respect privacy? And these are called mechanisms. Okay, so these are called mechanisms because they'll have randomness in them, and they'll decide, okay, I'm not going to give you the exact average, but I'm going to give like a perturbed answer and so on. All right? Okay. So what's the guarantee that we want? So the guarantee that we want is, suppose you have your mechanism M. And this is my database, right? All of the users' data, user 1, user 2, so on. From a user standpoint, when is an answer bad? Like for privacy perspective, when is the answer bad? Any guesses? Yeah.
The answer to identify it.
Right. If you can use the answer to identify the particular user, right? An even more extreme version of that is, actually the same version of that is if I can detect whether or not that user is present in the database. Okay, did I participate in the survey or not? Okay. Even that is some leakage of information, right? Imagine you have some survey on some rare genetic disease, and whether or not I participate in that study would reveal significant information about the person. Okay, so how could you mitigate that? I want to say you should not be able to learn anything about the user, including whether or not that user was part of the database or not. How would you formulate such a thing? Kind of seems weird, right? How would you say, okay, the answer should not change whether or not the user participated in the study? Yeah.
Have a distribution of all possible databases.
Mm-hmm.
The probability of getting a database with that user, is the same. The query doesn't give you any.
Right. That's one notion, but I don't think that's as strong because from my perspective, privacy should be absolute. Right? I'm okay with the errors having probability in them, like accuracy having some probabilistic guarantees, but the privacy should not depend on what the other users are doing.
Or I guess I mean like the distribution change or after the query.
Right. Yeah. So that kind of makes sense. So basically, we should not make any assumption about what the other user's data is, but we want something on the output. Okay. So in particular, I think what you suggested actually is what we're going for, which is just take the same database. Right? You have user 1, user 2, up to user n. Maybe, okay, so let's call the last user Alice. And let's replace the last user's data with some other user's data, some other data. Yeah?
Just
kind of. Right? But we had to be a little bit more careful on how we formulate the distance. Okay? So what we want is the answer to look similar, whether or not this person is Alice or the last person is Bob. Okay? So the answer that the interface gives me should not change much when I change a single user. Okay? So we want to say these two are similar when you change one user. Okay? And when we change one user, we'll call the corresponding databases neighboring databases, meaning all the records, meaning all the rows are the same except for one row where they differ. Okay? So formally, we want to say you have D comma D prime, which are databases with n users records. We'll say they are neighbors if they differ only in one row. Okay, So imagine, I take the same database, but swap one person for another person. From my perspective, that's good privacy if the answer doesn't change much, right? Okay. And it's reasonable to expect such a thing if you have a huge database. Maybe then the guarantee from each user, the amount of information you need from each user could be small enough to satisfy my privacy concerns. Okay, yeah.
How is this done? Like, are you, to use Alice and Bob as an example, was Bob a user that makes it somewhere else in the database, or is it?
Yeah, that's a good question. So you don't know if, maybe there are some constraints on what kind of vectors are allowed for users, but typically you'll just say, okay, take any other valid entry from the domain. That's it. Okay, so you're just taking this some domain where the records are coming from, like, they're real valued vectors. Maybe they're just like discrete valued things. Just substitute that for anything valid in the domain. The answer should not change. Okay. So intuitively, what we want is we want to say when I change one user, the answer doesn't change. So for two neighboring databases, M of D is similar to M of D prime. Okay. Now, the only thing that's left to do is to define similarity. So how could, what's one way to define similarity? Any suggestions? Yeah.
Guys here, but I know there's like the
Right. So, think of them as real numbers. You can say, okay, they should, those answers should look similar to each other. But even if the answer is just a single real number, right, then similarity could just be maybe they're close to each other numerically. Right. But as it turns out, that's actually not quite enough. People figured out how to attack it based on how to attack such things, based on, like, your answers could be very close to each other, right? But maybe your 16th decimal point is even if you're in the data set and is odd if you're not in the data set, right? So numerically, the two things are very close to each other. Okay. So, but from a privacy perspective, you can reverse engineer things. And as I said, it's not a theoretical thing. People did attack some release mechanisms using like floating point arithmetic. Okay. So what would be the right notion? It has to be much, much stronger than just saying, okay, if these are real numbers. Okay, so idea one, if real numbers, then ask for something like this. Is too small. Okay. Such a thing doesn't guarantee privacy as well as we hope. So for privacy, the guarantee that you really need, and that helps us kind of, we'll see later on, that helps us reuse things in a private way is the following. Okay, when you see it the first time, it seems a little weird, but it has some very nice properties as we will discover. Okay. Let me first define it, and then we will. So part of the challenge is just coming up with the right definition. And this was done by a work paper of Dwork, McSherry, Nissim, and Smith in 2006. It's a very important paper. It has won several awards and so on. And just for introducing this definition, more or less. Okay. So you have a mechanism M, which takes a database and gives out some answer. We'll say the mechanism is epsilon. Think of that as your privacy parameter. Smaller epsilon means stronger privacy. Okay. Epsilon differentially private. if for all neighboring databases, okay, so the output is taking some, values, right? It could be real numbers, it could be vectors, it could just be like, okay, zeros and ones, whatever, right? But if for all possible values in the range, the chance that the mechanism outputs y when you're given database D is close to the chance that the mechanism outputs y when you're given D prime as input. Okay. So imagine I'm looking at the 16th bit, right? You have 16th decimal point and say, okay, is the 16th decimal point 0? The chance that the 16th decimal point is 0 under database D should be close to the chance that something similar happens under database D prime. Okay. So you want these two probabilities to be close, and how close? They have to be close multiplicatively. Okay. So for all D and D prime, you need to have this. And if you have the upper bound, you also get the lower bound from the same logic. Okay. And think of this e to the epsilon as really just like a shorthand for 1 plus epsilon. And e to the epsilon works better when you compose things, instead of multiplying 1 plus epsilon multiple times, multiplying e to the epsilons is easier. Okay. All right. So you're saying the chance that my mechanism outputs a value is multiplicatively close to what happens under D prime and D. Okay. And as I said, e to the epsilon is basically like 1 plus epsilon. If you think of epsilon as being 0.01, they're always within small multiplicative factors. So to draw a picture, maybe you have something like this. Let's say you have okay, so let's say this is your database D, right? I plug this into my mechanism. The mechanism is not deterministic. It can add randomness to it. It's not always going to give you the exact average. It will give you some perturbed average. Okay. To preserve privacy, you need to introduce randomness. And let's say the output is like the real line. Maybe you're just outputting a single real number, then maybe the chance that you output 0 is something like this. Okay. And maybe the chance that your output half is something. I'm just kind of drawing the histogram of the potential answers under M. Right. So maybe the chance that your output 1 is this, 2 is this, 3 is this, 4 is this. Okay. The histogram of the probabilities of the different answers. Okay. The chance that M of D equals 0 is given by this. M of D equals 1 is this, M of D equals 2 is this, and so on. Okay. This is the probability of seeing each particular answer. And what do you want? let's say I change just the last row, right? This is D prime now with the neighboring database. What should happen? The picture should look similar for each right. So if you line up these two things entry by entry, the chance that the height of the zero bar here should be close to the height of the zero bar there, right? Every probability should be very close. Okay. We can imagine something like this. So what you want is that the heights are within e to the epsilon of each other. Okay. Every outcome should be pretty much the same, have the same likelihood under both of the two databases. All right, it's a seemingly very strong guarantee. Okay. Any questions about this? Yeah.
Similarity is like.
For each outcome, you want it to be similar, basically because you want to preserve privacy even when you could be a rare person. Maybe my query is tell me the salary of, what's the average salary of someone who is 100 years old? Maybe there's only one person in your database who has 100 years old, right? So then, even then, you want your privacy to be respected. Even for outliers, you want the privacy to be preserved. That's why you need it for every possible outcome, not just for things which are likely, but even for things which are unlikely. Okay, in fact, it's more important in some sense, maybe sociologically speaking, but yeah, you're doing it for every possible outcome or every possible answer that you could get, the chance should be similar. Okay, any other questions? So the interpretation, as I said, is you're saying e to the minus epsilon times this okay, and you should think of both of these things as really just 1 plus epsilon and 1 minus epsilon. All right. Okay. Since introduction in this paper, differential privacy, people have studied, like starting with this definition, when can we build such things? For what kind of queries can we build mechanisms which satisfy this strong guarantee? If you satisfy this, what happens if I reuse the answers for something else? So can I reuse things while not destroying privacy? And it's also found reasonable adoption in the industry. Okay, maybe not exactly this model, but variants of it where you look at like things like local differential privacy, shuffle differential privacy, and so on. Apple has implemented differentially private sort of statistics release in some cases. Google uses it in some situations. Microsoft uses it. And most recently, US Census Bureau actually used it for the 2020 census. Okay, so they built an interface where you can query it and the answers would be released in a differentially private. Okay. All right. And we'll also see, like, even things like PyTorch, TensorFlow. Obviously, you can't use it for very large databases, but you can have differentially private versions of gradient descent, differentially private versions of stochastic gradient descent, and so on. So instead of training, you could say, okay, use differentially private versions of these things to train my model. All right. It will guarantee that you learn the model. I'm releasing the model. The model is going to respect differential privacy. Okay. Again, this is not a theoretical scenario. I think at some point someone released a model, like a large language model, or whatever, I forget. But then from that model, someone could extract the address and SSN of some other person. Okay, just from the weights. Somehow it encoded it in some way. By giving a suitable query, you could extract it out. Okay, you want to prevent such things. Okay. All right. Yeah. Mm-hmm.
If that all iron kind of like noise, like the pushing or something.
Not necessarily. I mean, as I said, it's a very strong guarantee, right? You're saying the privacy should be preserved no matter what the other users are doing. Okay, so that's where I think, that's why it's not an issue, because no matter what the other users are doing, I'm still fine. It's, you can relax the constraints in some cases where you don't expect the other users to be malicious. Right? I mean, you can imagine there's a coordinated attack where the other users give data so that when you ask the query, only your answer will really come out. Like imagine you're going to ask, okay, tell me what's the max salary. And somehow everybody says salary is 0. And then when you get the max, you know that it's going to be your salary. Right? So the privacy should be preserved irrespective of what the other users do. There are more relaxed versions where you don't assume such malicious things, but for the first cut, we should start. Okay. All right. And so some points about differential privacy. You can debate whether this is necessary or this is enough for your privacy concerns. But the most important thing, which is already a big win, is that it is quantitative, right? It is a mathematical definition, and you can say, you can give a proof that my system, my mechanism will satisfy this guarantee. Maybe you're happy with it, maybe you're not happy with it, but it's much better than saying, okay, remove the names of the users, you cannot recover them. Yeah.
So given this kind of definition, distance define the optimal transport.
I think the issue with optimal transport is it's not multiplicative. It's like additive, right? If there's a rare event, then if an event occurs 1 in 100,000 times, and in the new distribution, the outcome happens 2 in 100,000 times, then both will be reasonably close, right? It's additive. Whereas in terms of privacy, differential privacy would say your privacy is pretty bad because it's looking for this multiplicative gap. Right? As I said, because you want to say even under rare events, I preserve the privacy. Yeah, that's a good question. The main difference is additive versus multiplicative. Okay, and there is an additive version that we'll talk about later, which is somewhat connected to it. Okay, so I say, the first win is differential privacy is quantitative. You're going to say something is private, quantify it. We can debate about whether it's good or not later, but first define mathematically what you're trying to achieve. Don't just say I removed the name, so it's anonymous, or I anonymized it by something else. Okay? And in particular, small epsilon corresponds to better privacy. Okay. And maybe you can typically think of epsilon as like roughly 0.01. Just keep. Okay, so for just if you want some concrete parameter, think of it as being something like 0.01. Okay. And as I also said, is a worst case guarantee over the databases. As we will see, we want the privacy to always be worst case, irrespective of the database, like whatever, irrespective of what the other users do. Accuracy, we will allow assumptions. That's fine for us. Okay. And probabilities are closed multiplicatively. And this is something to keep in mind. And that's why this is a very strong notion. Even rare events, you need to be very close. Okay. And as I said, e to the epsilon versus 1 plus or minus epsilon is just convenience. Okay. All right. Now that we have a concrete model, we can ask, are there mechanisms like this for some reasonable statistical questions? Okay. And so let's start with the most basic one, just as we did in the last class, which is, okay, how about computing the mean differentially private? Okay, so we'll start with this as the most basic question, right? And then we'll do many more things. So what do you mean by computing the mean differentially privately? It's the same setup as before. You have some n supposed to be a rectangle. Here you have user 1, user 2, so on, user n. And let's say each person has just like x1, x2 up to xn, a single sort of field which is binary, just 0 or 1. Okay, so this is my database, and this whole thing is held by a trusted curator. And then someone comes and asks what is the mean? Okay, and then we have to send out an answer. And we have to do this in a way which is differentially private. Okay. So in sort of differential private language, what you're trying to do is build a mechanism to answer to compute the mean, which as a function of the database is just this. Okay, so this is the function that the analyst wants to know the answer to, right? And that's what we're trying to compute differentially private. Okay, you'll say I'm computing it differentially privately in the sense that what I output will be some kind of approximation to the true answer, but it'll always satisfy the differential privacy guarantee. All right. And in the setup, we can ask two things. The first one is, we already saw something along these lines, right? We saw one sort of candidate for releasing the mean in some sort of private way, which was randomized response. Right? We looked at it in last class. There is a way you randomize the responses and then do some correction on the new responses, compute the mean of the responses, then do some correction. You get some kind of approximation for the true mean. Okay. So the first question is, okay, what guarantee does randomized response provide? What guarantee in terms of differential privacy does the randomized response mechanism provide for computing the mean? Okay, so just to recall, what was randomized response? So imagine you're the curator, someone comes and says, okay, what is the mean? What does the curator do? The curator says, okay, let me define yi is xi with probability 1 minus gamma, 1 minus xi with probability, sorry, half plus gamma, half minus gamma. And then you output f bar of x, which is, let's say, whatever we had from the last lecture, right? So remember, we had to do some correction, right? So this guy. Need to be consistent. Let me call these things xi bar. Okay. So this is my mechanism, yeah?
Because we have probability here, like different times.
Yeah, you would get different answers in each time. I mean, that's kind of necessary, actually. You need to have randomness in your mechanism, otherwise there's no privacy, because once the person changes, your answer could very well change. Right? And that can help me determine whether or not I participated in the survey. Right? Even that is what we're considering sensitive, right? Any change can tell me whether or not a person participated in the survey, which is sensitive information. Okay, so it's kind of a strong guarantee. We can consider various relaxations later on, but that's a very good guarantee. Okay, so this is what randomized response mechanism does, right? If you ask me for the mean, I'm going to compute these noisy versions for each point xi, and then release this estimator, this kind of correction to the mean. Okay. And the statement that we had from last class was about the accuracy of this, which was, okay, we said, probability that m of x minus f of x, which is a true mean, is greater than or equal to 1 over gamma times square root n, is less than or equal to 1 over 4. Okay, this is what we have. All right, so we have some kind of guarantee in terms of accuracy, but how about privacy? Is it differentially private? If so, with what kind of parameters? Okay, and it turns out that randomized response is actually a reasonably good candidate for differential privacy as a first attempt, at least. In particular, randomized response is is differentially private with some constant times gamma. That's the privacy that you get. Okay, so which kind of corresponds to our intuition, right? So we said if gamma is 0, then you have very good privacy because everything is the same. It doesn't depend on the data set, and it's kind of supported by this state. Okay, if gamma is 0, you're saying you have 0 differential privacy, meaning you have perfect privacy. Gamma is a half, you lose something. Okay. All right. Does the statement make sense? We'll try and prove it next. Okay. And in fact, the proof is by comparison, right? You have, let's see what happens, right? So what do we want to do? So you want to compare what's the chance. Now you have your original database D, and then you have your database D prime, right? This is your x1, x2, up to xn. You have your x1, x2, up to something, and maybe you're changing some ith coordinate. Okay, so this is some xi, whereas this is some xi prime. Okay, I'm changing the ith coordinate. So these are two neighboring databases which differ in the ith coordinate. Maybe in the first database, the ith coordinate is 0. In the second database, everything is the same except the ith coordinate is 1. Okay. And what does the mechanism do? It transforms this into you have x1 prime. Right, you add noise to each coordinate, but here this is a special one where they differ, so these two could still differ, right? So between these two, kind of every coordinate has the same distribution except the ith coordinate, right? Because they were starting from different things, and then you're doing some randomization, so the distribution could still be different. Right? And now what do we want to know? We want to compare for all possible answers. The answers are real numbers, right? You're computing some real number and releasing it to the people. For all possible answers A, we want to say the probability that you output A under the first case is close to the probability that you output A under the second case. Okay. And as I said, this is the only entry where we have a mismatch. And everything else is the same. So how can I compare these two probabilities? Any suggestions? I'm outputting something based on this and based on this. They are essentially the same in all the coordinates except in the ith coordinate. They only differ in one coordinate, right? Yeah.
Are we restricted then back to 0?
Yeah, I mean, randomized response, we defined it only for 0 or 1, right?
Then the probabilities are just at 1.
Exactly, right? So I think it makes perfect sense. So essentially, imagine that you're starting out with a 0 there and a 1 here, right? But you're doing randomized response and you're adding noise to it, right? Even if you're starting with different values, when you add noise, because of the noise, they could become the same. Right? And once they become the same, the answers will match exactly. right? And it's basically like saying, imagine, you have all of you. There's one person whose true answer was 0, but I'm flipping it to be, 0 with probability like 51% and 1 with probability 49%. Right? And in the other case, the coordinate was 1. There, you get 1 with probability 51% and 0 with probability 49%. So they should match reasonably often. So increasing the chance that they match. And whenever they match, you will be fine. Okay? So if xi bar equals xi prime bar, then the answers will match. Okay. So and what's the chance that the answers match? You can do some, sort of calculations, which I'm going to spare you. It'll exactly equal this. Okay, so whenever the answers match, everything matches. And what's the chance that xi, maybe let me write down a step 4 to check. Well, okay. So from a 0, well, okay, here, let's see. If this was a 0 and this was a 1, the chance that I stay from 0 to 0 is half plus gamma, right? But then the chance that I go from 1 to 0 is half minus gamma, right? So there's a good chance that I'm going to match, chance being half minus gamma, right? So if you work it out right, use Bayes' rule, which I'm going to spare you, you get this bar. For instance, if gamma is 0, then the distributions will be very close. They're just exactly the same distribution. So the ratio will be 1. Otherwise, they're like half plus gamma divided by half minus. Okay. And you can write this as this much. Okay. And as I said, you should think of e to the epsilon and 1 plus epsilon as really interchangeable, right? And so this is basically at most e to the sum 4. All right. All right. The question, doesn't the expected value of m of d and m of d prime also depend on the... Yes, it could depend on all of the other coins. We're not saying this is an exact equality here, right? We're just saying whenever the answers match, when the flips make you match here, these two coordinates match, the answers will match. And the remaining coordinates are all the same. So you can assume you're starting out with the same sets there. In the neighboring databases, you're only changing one coordinate. So even if they depend on all the other values, they're the same values between the two flips. Any questions?
F has like one-to-one correspondence with it. That's
Right.
not the case.
I mean, it can, f meaning the mean function. Yeah. So the mean function is simple enough for this to work, but it actually is okay even more generally, as long as your function is somewhat sensitive. I mean, we'll get to that later, and the various properties, if we can show something similar. Okay. It definitely does hold more generally, not just for f. Not just for the mean function, it can also hold for other functions. Because what you're saying is with this half plus gamma or half minus gamma, what you're working with is change. Right? So let me do a quick summary. So what did we learn from this? Right, so summary, randomized response with noise rate gamma is O of gamma differentially private, and is within error 1 over gamma square root n with probability 3/4. Okay, so remember, we also have some control on the error deviation. The chance that the error is more than this 1 over gamma times square root n is 75%. Again, this 3/4 is like a rough benchmark. You can tweak it further. If you want it to be 9/10, you instead of having 1 over gamma root n, it would be some other number here. But let's just pick something so that we can compare stuff. Okay. So let me rewrite the same thing here. So in some sense, what randomized response is saying is, suppose I want epsilon differential privacy, and my answer to have error less than or equal to some alpha. Okay. Suppose I want privacy 0.01, and I want my error to be also be like 0.1. I'm trying to estimate the mean. I want it to be within 0.1 of the true answer, but I also want to achieve privacy, which is 0.01. Okay. So what does this mean? It means, what should I take gamma to be? Maybe you take gamma to be like epsilon over 10. That would satisfy the privacy constraint. But then if I set alpha to be 1 over gamma root 10, this would imply my n is roughly right. So meaning to have epsilon differential privacy and error less than or equal to alpha, randomized response needs the size of the database to be bigger than or equal to something like 1 over epsilon squared times alpha squared. Right. So there's always a tug of war. If I want privacy and accuracy, if I just want accuracy, you need your data set to be somewhat big. But along with that, if I want privacy, I need my data set to be even bigger. And so there's a privacy cost in terms of the size of the database. Okay, that's the price of privacy. If you want to you want to privately release the mean, you need a bigger data set. Okay, The number of entries in your data set should be like 1 over epsilon squared times alpha squared. Okay, so that's the trade-off, that you should, quantitative thing that we should keep in mind. If I fix the privacy and the accuracy, how many people do I need to satisfy both of those constraints? If we have more and more people, privacy becomes easier to, privacy and accuracy together. All right. So a question, of course, then is, can we do better in terms of the size required per mean? Is randomized response the best, or can we do better than this 1 over epsilon squared alpha squared? Is there a better mechanism than that? Okay. And remember, this is all just for computing the mean, which you always take for granted, right? You just average things out. But even that, there's a nice question that's left open, which is this the best possible? Okay. Any questions about this? All right, we'll see that actually randomized response is not the best possible. You can, in fact, do quadratically better than this, which is typed. All right, okay. So to do that, let me sort of describe one of the more important mechanisms in differential privacy. Before that, let me kind of paint a general picture of how people get privacy. Okay, so by and large, there are two techniques for differential privacy. So there's sort of two high-level methods for getting privacy. One is called input perturbation. Input perturbation is what the name suggests. What do you think it is? Yeah. Exactly, right. Right. So what the curator is going to do is you take your database, this is your database X. I'm going to perturb it some way, like some noisy version of X. Okay, and then answer something based on the noisy version. Once I perturb it, I'm only going to work in this perturbed model and then release some function f of noisy. You perturb the input and then just work with the noisy database and then release the answer. Okay, yeah.
Randomized response.
So randomized response is actually exactly of this type. Okay. And in some sense, this is a kind of maybe a more desirable setting. This is called database sanitization, where you take your database, just kind of perturb it, and then potentially you can release this perturbed thing and just kind of work with that as a substitute from now on. You're doing building some heavy machine learning model, do the same thing as before, but just work with the noisy version instead of the actual version. Okay, that's input perturbation. All right. And if there's input perturbation, what else can we have potentially? Output perturbation, right? So here, what the curator does is, you take your X the curator actually computes whatever f of x that you're interested in. Okay, exactly. But then releases f of x plus some noise. In some sense, the curator is fudging the output. You compute the output, fudge the output, and send it out. Okay. Two different works. Now, each one has its own advantages. You might say, okay, this is better because this way, I don't have to do the computation of the output. Right? Maybe it's a massive ML thing that I cannot run myself, but I can, do this perturbation, send it out, and that person will do what they want. And this is like, just you usually get better guarantees. Okay. So we already saw randomized response, which is an input perturbation style mechanism for computing the mean. And now let's see an output perturbation mechanism for computing the mean. Right? So, and this will lead to what is called the Laplacian mechanism for computing mean. Right. So once again, remember what's the input? The input is a bunch of values which are all in 0, 1. And you want to release the mean. So what the mechanism does is, okay, so first you compute the function exactly. Okay. And then you release the output plus some noise. Okay, I'm going to perturb the output and release the noise. And it was maybe even simpler than randomized response in hindsight. Right? Just release a noisy version of the output. Okay. And this is called the Laplacian mechanism because of the specific noise that you add. It turns out that the right distribution of the noise, you might say, okay, maybe I'll add some kind of Gaussian noise. That does okay. But the right mechanism of the noise turns out to be, you should use right distribution of the noise, as it turns out, is actually what's called the Laplacian distribution. Okay. And what's the Laplacian distribution? It's a distribution, right? So let me state that. If you think of the Gaussian distribution, it has mean 0 and then variance some parameter, right? Sigma squared or something. Similarly, Laplacian distribution will have typically mean 0 and variance, let's say B. It's kind of a strange notation. I don't know why statisticians shows it. They denote variance by B instead of sigma squared as you would do for Gaussian, but that's what we have. So let's work with that. Variance B is the distribution where the probability density function is exactly this. Okay, I'm writing down the exact probabilities. The probability takes the value, oops, should be a plus. The probability that it takes the value 0 is exactly 1/2b. The probability takes the value 1 is like 1/2b times exponential minus 1/b and so on. Okay. Little bit like the Gaussian, except you don't have the square. The square is missing. Right? And pictorially, maybe it looks something like this. It's a univariate distribution, right? And as b gets higher, it gets more and more spiky. You can imagine maybe this is b equals 1, maybe. B equals 2 could be something like this. Oops. B equals 3 maybe looks even more spiky. They all have exponential decay. I mean, they should not hit 0. So they're all like exponentially decaying. They're symmetric about the negative and positive values. So their expectation is 0, and their variance is always b. Okay. Any questions? I mean, you can wonder why this and not Gaussian, but as I said, you can work with various distributions. This turns out to be the right one because it kind of scales well with the e to the epsilon and fits everything like a glove. All right. And this is called the Laplacian mechanism. And what can we say about the Laplacian mechanism? We claim that it's reasonably straightforward to show is the following. The Laplacian mechanism, meaning you compute the output and then perturb it by adding Laplacian noise, is if I choose my variance parameter b to be 1/epsilon times n. Okay, satisfies epsilon differential privacy for releasing it. If I just add a Laplacian noise, then I get this differential privacy for releasing it. So now you can imagine if you're the US Census Bureau and you're building this API, the kind of queries you allow are typically like average. You might, we've been talking about the mean a lot. Why? But it's one of the basic sort of primitives that you want to allow for database. Right? You might say, okay, tell me what's the average age within a zip code. Now that is itself a mean query, but within a subset of the database. How would you solve that? I would compute the actual mean and release the answer with some Laplacian noise added. Okay. And the same thing for everything else. You can also do this for like conjunctive queries and so on. You always just compute the answer, do some Laplacian noise after. All right. Okay. So what does this do? Okay. So remember, so m of x is the actual mean plus some noise, right? What the mechanism releases is the actual mean plus z, which is sampled from this Laplacian with some parameter b. Okay. And the proof really hinges on the following thing. And what is m of x prime? M of x prime is f of x prime Let's see. Right, where x and x prime are neighbor, meaning they differ in only one coordinate. So here's a question. If you have x and x prime differing in one coordinate, how big can the gap between the means be? How much can the means differ? Yeah. Yeah, so it's at most 1/n, right? You're differing in one coordinate, so the gap is going to be at most 1, but then you're taking the average, right? So the average is only going to be different, only going to differ by 1/n. Okay. So in some sense, why bigger databases give us better privacy, right? Because when I change 1, the answer doesn't change as much. Okay. And if you think of these two distributions now, m of x and m of x prime, what do they look like? Right? You have 0 and you have f of x. Okay. What's the distribution of m of x? The answers that you would get under the first database? Well, by definition, it is still a Laplacian distribution, except it's shifted. The mean is now not 0, but it's f of x, right? So the PDF, the histogram of that should look something like this, right? And f of x prime should be nearby. It's pretty close. I'm going to draw them far because it's hard to draw very small things. F of x prime is nearby and the gap is only 1/n, right? And what can you tell me about the distribution of m of x prime? It's still going to be Laplacian, except it's shifted. So the mean is not f of x, the mean is f of x prime. Right, so you have this is the distribution of m of x, and this is the distribution of m of x prime. Okay. And what are we interested in terms of differential privacy? We are really interested in comparing the heights at any 2 points, right? We want to compare take any point, what is this probability divided by the bigger probability and so on. And that's what we are trying to do. Okay. And intuitively, the reason Laplacian mechanism works is when I shift it a little bit, the heights don't change much. Okay. It's decaying exponentially, but not fast enough that when I shift it a little bit, you'll be able to tell the difference. Okay. So in particular, we can exactly compute everything. So the probability that m of x equals a is probability that right, which is 1/2b times e to the minus. Okay, this is by the definition of the Laplacian distribution. Yeah.
Like the factorial distribution.
Yeah, more or less. I mean, you need the distribution to be smooth, right? And it's not about the tails, but just that the PDF should be smooth. Okay. And you want it to have the reasonably decaying tails so that you get good accuracy. Right? If it has very, very wide tails, then it's not good because the accuracy could be terrible. Okay. And if I do the same calculation for the other case, when you have the neighboring database, I get kind of the same thing. Okay. So almost any distribution which is reasonably smooth would work, but Laplacian distribution, as I said, makes the arithmetic really clean and simple. Okay, so in particular, you have these two expressions. So what's the ratio? The chance that I see a particular outcome A under the first case versus the chance that I see the other outcome in this distribution A in the case of X prime. I just have to take these two ratios. Okay. So the 1/2b goes out. I get e to the minus a minus f of x by b divided by e to the minus e minus f of x prime by b. Okay. Which is all right. And as we said, this gap is at most 1/n, right? Because the means f of x and f of x primes, they differ by at most 1/n. They're pretty close to each other. Okay. So you just get if we choose b to be 1/epsilon n, I just get exactly e to the epsilon. All right. Yeah.
So shouldn't this be like the ratio of density? As it's like,
No, this is the ratio of the probabilities, right? Probability density function.
it's a continuous distribution.
Oh, okay. I see what you mean. Instead of writing probability, I should write the PDF. Is that what you mean? Yeah. That's what this notation is for, right? I mean, yeah. But let me not go into PDF versus probability. Just think of it as what integrates to what. Okay. What's the PDF of m of x divided by the PDF of m of x prime? That's what you get. Okay. All right. So definitely, if I do Laplacian mechanism where the variance is like 1/epsilon n, I do get epsilon differential privacy. Right. So if we figured out one side of the equation, which is you do this noise, you get privacy, but privacy we also have to compare what it does to our accuracy, right? So how about accuracy? Okay, so remember, we are releasing f of x plus z, which is Laplacian. Okay, so we're adding some noise to the outcome. How big is this noise going to be? Well, for the Laplacian mechanism, the tails are very nice. Okay, they have exponential tails in the sense that the probability that it takes a value bigger than t times b is at most exponential. Okay, kind of shows here, the PDF is decaying exponentially. If you do the integration right, then you can show that the chance that I take a value which is more than t times b is exponential in minus. So in particular, the probability that it's more than 2 times b is at most exponential minus 2, which is 1/4. Right? So meaning, so what does this tell us? Laplacian mechanism with b is 1/epsilon n is epsilon differentially private, and the chance that your answer differs from the actual value by more than 2/epsilon n is at most 1/4. Right? The chance that it's more than 2 times b is at most 1/4. Okay. So what does this mean? It means that to get epsilon differential privacy and accuracy alpha, we need n to be, if I said this to be alpha, you need n to be 2/epsilon. Okay. So if I tell you, okay, give me something which is 0.01 differentially private and achieves accuracy 0.1, you can do this with the Laplacian mechanism as long as the number of users is at least this 2/epsilon times alpha. All right. And how does this compare to randomized response? So randomized response said, to get epsilon differential privacy and accuracy alpha, you needed n to be some big constant times epsilon squared alpha squared. Okay. So randomized response required a quadratically worse number of users compared to Laplacian mechanism. Even though it looked like a good thing to do at the beginning, it's not as good as Laplacian mechanism. Okay. Any questions about this comparison? All right. And there, it is possible to show that this is in fact the best possible. Right. If I want epsilon differential privacy and accuracy alpha, we cannot do better than these many users. All right. Okay. So far everything seems, I'm okay, this is good. We learned how to compute the mean differentially privately. But what we should think of now is, can we generalize this to not just the mean, but maybe more complicated functions? Maybe I have a database and someone wants to compute the first principal component or something close to the first principal component. Can you do that differentially private? Maybe I want to compute not the mean, but the median. Can you tell me that differentially private? How about the 10th percentile? How about the 90th percentile? And so on. In fact, one of the main things as a database curator you worry about, or you have to deal with, are sort of this percentile statistics questions. Give me a histogram of this particular coordinate. Give me a histogram of all people in your database who have diabetes above age 60 and had a cardiac, incident in the last year. Right? These are the kind of statistics that, let's say, if you're in a hospital, you would like your analyst to have. Right? Can we do all those things differentially private? Yeah.
As we can bound the range of the output, we should.
Exactly. So Laplacian mechanism is somewhat generic, right? If you think of this analysis, where did we use the fact that f was the mean? Only in this equation. This was the only part that f being the mean played. That when I change a single point, the answer doesn't change much. Right? So that's one nice thing about sensitivity, that even though when we're studying about the mean, actually about Laplacian mechanism, it actually works more generally, and we can quantify it by the following. Okay. So this is sensitivity. And what does it say? Now, if I have a function on my databases, the sensitivity, I'll call it S1 of F. Is just the max difference in the outcomes of two neighboring databases. Okay, it's a function with real valued outcomes. It could be the mean, it could be the median, maybe it's the 10th percentile, 50th percentile, whatever you have. And you're just looking at what's the difference between two neighboring databases. If I change one coordinate, if I flip the data of one user, how much does my function change? And intuitively, if your function is very sensitive, right, then it should be harder to get privacy against such queries, right? If my function is just saying, okay, tell me the age of this particular user, right? Then you cannot get privacy for that question just because it's highly sensitive. If I change one particular coordinate, it would change the answer completely, and obviously you cannot get privacy. Right? So this is one way to quantify what makes for nice functions for which you can, release queries while respecting privacy. Okay. And as we saw, the sensitivity of the mean function is at most 1/n. And in the setting before, when you change a single coordinate, the mean only changes by 1/n, where n is the size of the database. Okay. And if you're just, looking at your analysis, nothing changes. If I have any function f, not just the mean, as long as the sensitivity is at most some s, then Laplacian mechanism, where you compute f of x and add noise, achieves epsilon differential. Okay, so I just need to add noise, which is kind of scaling with the sensitivity. The smaller the sensitivity, the less noise I have to add. The higher the sensitivity, the more the noise. Okay. Any questions? The same argument works, nothing changed. I mean, in fact, that's what we did just before. And more generally, the same sort of thing works not just for functions with univariate outputs, but even if you have multiple outputs, right? I can say, okay, in your database, maybe I don't have just a single coordinate for each user. I have x1, I have x2, so on. Okay, and I want to compute f, which is k numbers now. Okay, you have your database. I ask, okay, what's the average age, the average weight, average height, maybe the median income, and something like that. All kinds of stuff. Okay, and you can still define sensitivity. Take any two neighboring databases, two neighboring databases. How much do the answers differ for two neighboring databases? So for each coordinate, add up the possible differences. Okay, so that's the definition of sensitivity now for multivariate functions. Right? And we can generalize Laplacian mechanism also to multivariate functions. Right, so you'll say compute f of x. Okay, and how would you generalize it to multivariate things? You know, we did it for a single coordinate. If you have multiple coordinates, what should you do? Yeah,
Add a Laplacian.
each coordinate, just add independent noise. Okay, so compute k independent Laplacian noise variables, z1, z2, ck, which are Laplacian b, right? And then you output f of x plus c1, c2 up to c2. Okay. And you know what we just saw, the argument which worked for the univariate case, which also worked for when you have sensitivity bound, also works for the k-dimensional case. Because the probabilities are independent. When you take the ratio, everything kind of nicely multiplies, and you get the following. If I have a function like this, which has sensitivity, then Laplacian mechanism with noise rate epsilon differential privacy. Okay, and the proof is similar. You just have to write the probability that m of x equals a1 through ak okay, these are independent coordinates, so the probabilities multiply, and then everything works as it did before. Okay. All right. So let me summarize what we did so far. So in summary, we now have a seemingly good notion of privacy, quantitative, kind of, you can prove that it's holds or not, and it seems to give, it makes intuitive sense, right? Again, you have to decide whether or not it's acceptable for each user based on other considerations, right? You make the definition, you quantify, this is what I'm going to achieve, and then say your algorithm satisfies this, right? And we said randomized response has some differential privacy, all right? And then we also saw that Laplacian mechanism, which is kind of a foundational mechanism in that you can build many other more complicated things from this, okay? From sensitivity. So as long as I have a sensitivity bound or global sensitivity, it's I'm calling it global sensitivity because the guarantee on the condition on the sensitivity is over any two worst case databases. Okay, so as long as I know that the function values don't change much, I have this nice property. Okay, so then I can get differential privacy and so on. All right, any questions about this? So what we'll do from now on is we saw an example of differential privacy. We defined it and then we saw some mechanisms to get it. Now we'll see how to use it. Right? If I have something which is differentially private, what happens if I do some post-processing? Right? Can I say something if maybe only one user is corrupted versus maybe several users want their privacy to be preserved? Maybe I don't have just one record in the database, I have 10 records. How can I handle that? Right? Maybe my, like if you're a health insurance company, right? Then maybe all of my family's records are treated separately, but leaking any one of them is bad for me, right? That's called group privacy, meaning I don't want it for a single user, but I want it for multiple users. Is there something better we can do there? And for other kinds of queries, Laplacian mechanism is not the best. So we look at other mechanisms, something called exponential mechanism and other stuff. Okay, so that's what we'll do in the next lecture. All right. And just a reminder, assignment 3 will be posted today. Okay. All right, let's see you on Monday.